Pure substances are an important thing that we will work with in the class. You have to understand what they are. You may think that a pure substance is like, you go to the store and you buy a bottle of water and it's pure water. Well, technically in the real world, the supposed pure water would be bad for you if it was actually pure water. You want some of the impurities in it, but that's beside the point. When we say pure water in this course, or pure substance, anything pure, we don't mean that it's safe for you to drink. We don't mean that it's healthy. What we mean is that it is a fixed or a uniform homogeneous chemical composition. So it's what it's made up of does not change with time. So not only does it not change with time, but it's the same throughout, which is what uniform gets to. Now think about nitrogen. If you have a bottle of nitrogen, is it a pure substance? Well, nitrogen is one chemical species. As the nitrogen bounces around, it's not like there's something in one side and something different in another side. So yes, nitrogen would qualify as a pure substance. What about air? Well, you might think that air is impure because it has nitrogen and it has oxygen and maybe some pollution and some carbon dioxide. Who knows what all it has in it? So definitely not pure, correct? Actually, no, that's what we would call a pure substance. Again, don't mean that it's necessarily good for you to breathe air that's heavily polluted, but as long as the chemical composition of that air does not change and it's uniform wherever we look inside of the system, then it's a pure substance. So air, even dirty air, would qualify. Now, if we have air in a room, let's say, maybe not in a room, maybe in a space, and that air has ash in it, and the ash falls out, well, then there's a different chemical composition in one area than in the other, and then it wouldn't qualify as a pure substance. However, in most cases, air would be a pure substance, even though there are traces of inert gases and other things as well. I should say noble gases. Obviously, nitrogen is typically inert, though it can react. What if we have water? So let's just imagine a container that has only the chemical H2O, dihydrogen monoxide, if you want to make it sound scary. So we've got a container with dihydrogen monoxide. Is it a pure substance? Well, what if there's two phases? So there is a vapor in one area, what we'd usually call steam, and liquid water in another area. Well, that is still actually a pure substance. The reason is because we don't care about phase in this definition. All we care about, oh, by the way, we don't care about concentration either. All we care about is that the chemical composition is uniform, and therefore water would qualify. What about if we had air and we were beginning to liquefy it? What about if we were cooling it down, cryogenic distillation, whatever the process may be, where we're trying to separate the nitrogen and the oxygen from one another? Is that a pure substance? Well, here you have to think a little bit deeper. You have to understand that nitrogen and oxygen have different boiling points. Therefore, the liquid would be rich in one, and the vapor would be rich in the other. Therefore, they do not have the same chemical composition. They are different. And therefore, air that we're, liquefying would not be considered a pure substance because it's the chemical composition that we care about the most. There are obviously three primary phases. You should already be familiar with these: solid, liquid, and gas. Not really a big surprise. But have you ever thought about the bond strength in them? I mean, if you tried running your hand through a piece of ice, it probably didn't work out very well, right? That means that the molecules are bonded together well. You don't have enough energy in your hand to push through them, or enough strength for that matter. Now, if you add energy to ice, what happens is that ice will move into a different phase. It will melt and become a liquid. Therefore, but remember, I'm jumping down to energy. So ice has low energy. Liquid must have more energy because it requires energy to move from from solid to liquid. We put energy in to get it to make that phase transition. So the amount of energy in the solid is low, in the liquid is medium, and of course obviously in gas is even higher because you have to keep heating it. But what about bond strength? Well, you can run your hand through a tub of water, right? There's some resistance there, but you can do it. And so the bond strength in the liquid is typically medium instead of strong, whereas in gases you don't really feel steam. You might feel the heat transfer from the steam if it's at a high temperature, but you can certainly move your hand through steam with no problem. Therefore, the various molecules are not connected to one another very strongly at all. Now, order. Well, liquid water is not very ordered, but it's more ordered than gas. On the other hand, solid water, ice, has a crystalline structure, and therefore the order is fairly high. And these are general principles of not just water, obviously, but any substance. Speaking of phases, how do we identify phases? Well, the key thing is that there are distinct arrangements of the molecules. They are homogeneous, and we can see boundary surfaces often. These are the ways that we identify when there are two different phases in contact with one another, for example, or a difference between two phases. So if you look in a clear glass of water and you've got ice in it, you can obviously see the outline of the ice. You can see the boundary. There's a little bit of difference in the nature of the phases because, just by visual appearance, the liquid water is typically clearer than the ice itself. And so you can see a difference there. But also, there can be multiple phases that a chemical or an atom has that are the same type in terms of being a solid, a liquid, or a gas. Well, probably not a gas, but a solid, and maybe a liquid. Certainly solids. There can be multiple different solid type phases. So if you think about carbon, well, carbon can make the solid form of diamond or graphite. Both of those are definitely two distinct phases, solid phases of carbon. They have their different uses, right? I mean, diamond is obviously very hard and useful in that sense, and graphite is a good lubricant because the planes slide past each other. But they are both still carbon. They are the same element, the same atom making up those solid phases. But if we were to get a large vat and mix the diamond in with a whole bunch of graphite, you could probably pick them out pretty easily because of the distinct molecular arrangement that gives rise to different visual properties, and we give rise to boundary surfaces. It's not like the graphite's going to weld itself to the diamond all of a sudden. So you can see a boundary between the two. And of course, in studying steels and things, you've probably studied how there can be different phases of steels. You've probably used a eutectic diagram if you studied materials. So on to how water boils. I know it sounds like a very riveting topic, but it is important. You may think you know how water boils because you've boiled water on the stove before, but in reality there's some interesting things that happen. If you start off and you hold the pressure in or on the water constant, let's start off with liquid water in state 1, and you add thermal energy via a heat source, maybe a candle or something. Well, what will happen? Well, what is sensible? You know what happens. The temperature will go up, right? If you're at, say, an atmospheric pressure in 20 degrees Celsius, that's nowhere near the boiling point of water, and so you start adding heat to it, and the thermal energy of the water increases, and that thermal energy increase is reflected as an increase in temperature. Now you finally reach a magic point, at least it seems like that. There are reasons for it, but we won't get into the reasons in this class. I don't think I know them all. What matters is that we know that water will boil at 100 degrees Celsius. Well, do we really know that? Remember, we've assumed a pressure of 1 atmosphere. We're holding pressure constant at 1 atmosphere. If you take water to a high elevation where the boiling temperature is lower, the reason the boiling temperature is lower is because the pressure is lower at that area. If you increase the pressure, let's say you have a piston cylinder device like this, and you increase the pressure on the water, well, you will increase the boiling temperature. So the boiling temperature and pressure go hand in hand, and they're called the saturation temperature and pressure. And therefore, state 2, 3, and 4 are all three referred to as saturated states. As a matter of fact, state 2, where we have a pressure of 1 atmosphere and a temperature of 100 degrees Celsius, is referred to as the saturated liquid state. It's almost as if the liquid can't hold any more heat or can't hold any more thermal energy because it doesn't hold heat anyway by our definition in this class. but it can hold thermal energy, but it's like it's saturated with thermal energy like a sponge, and it has to release some of it somehow. And since steam has more energy in it than liquid does, well, then some liquid is transformed into steam and, experiences a phase change. So then we end up at state 3, and the interesting thing is that the temperature doesn't change. If you measure the temperature of the steam or the temperature of the liquid, you will find both are at 100 degrees Celsius. Now this is assuming that this is all going through a quasi-equilibrium process where there's no concentration of heat or thermal energy in one area. And so there's thermal equilibrium is what we're assuming. Now, if you do this experiment at home and you boil some water on the stove and you have a thermometer and you stick it in the water, you'll find that it's 100 degrees. If you take that same thermometer and you stick it in the steam, if you were measuring just the steam temperature, you would find that that steam was at 100 degrees. However, what you will find is that your thermometer will drop, and the reason it drops is because the steam is not just only steam. Rather, the steam has already mixed with air, and the reason you can see it is because it's already given off some energy to the air. It has condensed. That's what you see, are teeny tiny droplets. So you don't really see steam. Steam is actually clear. What you see are droplets that have already condensed and therefore can cool even further and are in the liquid phase. But obviously it comes off of the top of the pot in the gas phase. So anyway, the state 3 is referred to as a saturated mixture state because there's both vapor and liquid. It doesn't mean that the two are mixed in together. It just means we've got both of them in a container. If we keep adding thermal energy, what will happen is the temperature and pressure will remain constant. We're holding the pressure constant, but the temperature will remain at 100 degrees Celsius, and we'll finally get to the point where we've boiled off the last drop of liquid. And at that point, this is referred to in state 4 as a saturated vapor state. So all of the mass in the system, all of the water, for example, is in the vapor phase. Now, of course, we're talking about water in this example, but many substances behave in a similar fashion, having saturation points and points where they go from a sensible change, the temperature changes so it makes sense, to a latent change, a delayed change in temperature. The temperature change is delayed as we go from state 2 to state 4, from saturated liquid to saturated vapor. If we relentlessly continue adding thermal energy to the steam in state 4, then the temperature will start to increase again because there's no more liquid to change phase. And so then the temperature will begin to increase. Now that was very interesting. There's a little more to it. The region where the water is not close to boiling and it's still liquid is called the subcooled or compressed liquid region. I already told you that state 2 is the saturated liquid or about to vaporize state. Saturated liquid vapor mixture is present in state 3, and then saturated vapor is how we refer to something that is about to condense, that there's no more liquid but it's at the saturation temperature and pressure. And then the right-hand state, state 5, is referred to as the superheated vapor state. And of course, there's a constant temperature observed as the phase change progresses. Now, people get confused, or I think students get confused, because I tell them, what's the saturation pressure? Well, I can't ask you that without giving you some other information, because saturation temperature and saturation pressure go hand in hand. They're not independent things of one another. If you know the pressure at which like say you've got a pot of water on the stove, well, if you've got the lid off and you haven't sealed the pot, you have set the pressure by default because you're exposing it to local atmospheric pressure. Now, if that pressure is 1 atmosphere, 14.7 psia or so, then the temperature at which that water boils is set. It's 212 degrees Fahrenheit or 100 degrees Celsius. We all know that. We've learned that a long time ago. But if you change the pressure, if you somehow put the water into a container that can be sealed, and you can evacuate some water out, or some air out of it, or you can pressurize it, say with more air, that would work fine, then you will change the temperature at which the water boils. So saturation temperature and pressure is nothing more than just the pair that go together that represent when the substance boils. That's all it really is when it phase changes. Okay. So there is a table in the back of your book. You should mark at the back of your book. You've got both English and metric units, just as in our previous class. Metric comes first and then English is after. You should probably mark the first page of both with English and then metric, and then also there are tables of saturated water in there. I would recommend you find them. It should be table A4E, but this scan is from an older version of the text and he may have changed the appendices by now. I think this is from the 6th edition, so the 7th edition should be the same. In any case, you'll notice that if you want to know the saturation pressure, all you got to do is look up the current temperature and then read off the saturation pressure. So if we look up a temperature of 212, not surprisingly we find 14.7 or so psia as the boiling pressure. And so another way to say that is if I have water at 212 degrees and the pressure is above 14.7, it will not be boiling, whereas if it's at or below 14.7, it will boil. That's the boiling point. Okay. You could plot the boiling pressure versus corresponding boiling temperature, or so-called saturation pressure versus saturation temperature. It's not a straight line, but it can be plotted for whatever substance you're interested in. Notice that there are also saturation tables for R134A in the appendix, and you should at this point get tabs and mark all of those pages now, putting saturated water, saturated H2O if you want, and saturated R134A so that you can find them. We will use these tables extensively. Now, the amount of energy required to accomplish a phase change is called a latent heat. It's the amount of energy you have to add to give the, say, liquid enough energy that it all goes into the vapor phase, or, say, solid to go into the liquid phase. And it turns out, of course, that's the same amount of energy you have to remove from the vapor to go to liquid or liquid to go to solid. So I'm not trying to say, I probably confused you there, I'm not trying to say that the transition between liquid and vapor require the same amount of energy per mass as does the transition between solid and liquid. That's not the case. It's just going from liquid to solid, or liquid to vapor, you'd have to give a certain amount of energy, and going from vapor to liquid, you'd have to take back that exact same amount of energy for that transition, that phase transition. For water, if we're talking about 100 degrees Celsius boiling temperature, then the amount of energy is 2,257.1 kilojoules for every kilogram mass of water. Going between liquid and solid at 1 atmosphere, 0 degrees Celsius, the amount of energy is 333.7 kilojoules per kilogram. If I have solid water at 0 degrees Celsius and I give that water, and 1 atmosphere of course, and I put 333.7 kilojoules into each kilogram, I will have liquid water at 0 degrees Celsius, and vice versa, going from liquid to solid, removing the energy. I found the animated graphic in the upper right hand corner of the slides many years ago and really liked it. I wish I remembered where I got it from, but I was thinking it was a Purdue page actually. And I really like it because what it shows you is the boundary between the side of a little vapor bubble and the corresponding surrounding liquid. So it's on the right of that bubble. And I really like this because it's showing water. That's, the red sphere indicates oxygen and the two little white spheres indicate hydrogen. So this is H2O. And I really like this because you can see little molecules of water getting enough energy to go out into the vapor phase, but some vapor phase molecules that are zipping around coming back and giving their energy to the bulk water. So there's enough of these that happen, it's an equilibrium between the two. But the whole point here is that particular molecules gain enough energy to go into the vapor phase, and some vapor phase molecules land in the water and don't escape. So that's a really interesting thing. If we take that idea from vapor and liquid to solid and liquid, it's still true actually. Some solid ice in your freezer will get enough energy to go into the liquid or then onto the vapor phase. And that's what causes frost in freezers. Frostless freezers are just freezers that basically change out the air ever so often in the freezer so that the any water in the air doesn't have a chance to stick to any other surface, and so it keeps It's not as efficient necessarily, but it certainly does prevent the water from freezing on surfaces inside the freezer, which is a benefit. You don't have to clean it out anymore. Some of you may not have even realized you have a frostless freezer. Frostless freezers are the order of the day. The other type are not common anymore. Now, this should help you understand too what happens between solid and liquid when you put ice in a cooler for a picnic. Well, why do you do that? Well, obviously the cooler is set up to resist heat transfer, right? There's the styrofoam or some insulating material in the walls that is supposed to prevent, or at least it can't prevent, it can only reduce the rate of heat transfer into the cooler. And the idea of having solid ice in the cooler is even when that solid ice goes to 0 degrees Celsius, it will clamp the temperature to about 0 degrees Celsius, because as thermal energy infiltrates into the container, the picnic cooler, what will happen is that thermal energy will ultimately make its way into the ice and melt some of the ice, so that some of the ice will transition from solid to liquid. And so this latent heat diffusion is something that is quite a useful property in many different scenarios, and here's one for a picnic basket. Now, that experiment we performed where we put water in a container at a particular pressure and then added thermal energy and observed the phase change, that could be done at some other pressure. We ran that one at about 1 atmosphere, which is about 100 kilopascals. So that's roughly the 0.1 megapascal pressure curve. And this diagram is a temperature versus specific volume. So if we look at how much space is taken up in the container versus the mass, we can calculate the specific volume, and as long as we keep track of the volume of the container versus phase, then we can plot this out, and temperature as well, of course. So we've got one curve there. There are multiple curves, but let's concentrate on the 0.1 megapascal curve, which would be the atmospheric pressure curve. And let's note what happened. Well, we began with a fairly low specific volume, low temperature, saturated liquid, and then added thermal energy until we ended up at this knee in the curve where we had all saturated liquid. So we had subcooled liquid, now we're at the saturated liquid point. If we continue, now notice one thing that happened here is the temperature went up and the specific volume did change a little bit. It got a little bigger, a little less dense. Not much, but some. Enough that it's something I have to contend with in my heating system. I've got 1,000 gallons of water storage. It's not potable water, it's just water for holding thermal energy. And that water will expand as I heat it. It starts off at about ground temperature, 50 degrees, and goes up to about 200 degrees using the wood-fired boiler that I have, though it's not really a boiler. Anyway, so that water is going to expand, and if I didn't have an expansion tank that could accommodate the extra volume, well, either the tanks are going to give or the piping is going to give, something's going to give, because that water is going to expand. And so I had to take that expansion into consideration, even though my system's called a boiler, but it doesn't boil the water, it just changes the temperature of the water from subcooled, not even up to the saturated point. But the water volume is going to change as the temperature changes. Now, if we keep adding thermal energy to this saturated liquid water, what will happen is some of it will start to boil off, and we will get a saturated mixture of vapor and liquid. Again, it doesn't mean that they're mixed together perfectly or anything. They could be two separate, totally distinct phases, but from what we saw before in that animated graphic, hopefully you realize that they are in equilibrium with one another. In other words, some gas molecules turn into liquid molecules, some liquid turn into gas. But the rate at which each of those molecules leave their respective phases is the same. So there's no net gain or loss of either until we add more energy. And as we add more energy, then more liquid goes to more vapor. So we're moving to the right on this diagram. And of course, what happens is that the specific volume of the system increases. If we're just looking at the total volume of the system divided by the total mass, then that's really what we're plotting here. Now, something that's really important to understand, there are no molecules in there that have the density in the middle of that curve between those two knee points, between the saturated vapor and saturated liquid points. The reason for that is that all of the liquid has the specific volume of saturated liquid, and all the vapor has the specific volume of the saturated vapor. It's just the amounts of the two that's changing, right? The vapor is decreasing while the liquid increases, or if we're removing energy, or the liquid's decreasing while the vapor increases. So the average specific volume, sure, that changes, but the specific volume of the liquid and the specific volume of the vapor remain exactly constant. It's just the amounts of vapor and liquid that change. So we relentlessly add thermal energy until we get to the point where all of the liquid has boiled off and we now have all vapor. So we're at the saturated vapor point on the curve. Obviously now the specific volume of the system is the specific volume of saturated vapor at this point. Notice the horizontal movement of this curve, that it's all at one temperature during this process. Of course, since we're at roughly atmospheric pressure, this is going to be about 100 degrees Celsius. If we continue to add thermal energy, then we will move off up and to the right, where the temperature then continues to increase and the specific volume increases as well as we add more and more thermal energy, holding the system at constant pressure. Now we could repeat this experiment for many different pressures, and we'd find different saturation points, different temperature saturations obviously, and we'd also finally find a point where the liquid would, we'd be changing temperature, and then all of a sudden it would move and it would be a pure vapor and would just continue changing temperature. So we'd get to a point where the temperature just increases continuously rather than going through a latent change. The change from liquid to vapor is instant. And that point is called the critical point, and the temperature and pressure there are called the critical pressure, critical temperature. You could even talk about the critical volume, though we usually don't. Now, if we perform an experiment with a pressure above that, then that's called a supercritical pressure, and that would be a supercritical experiment. Now, if we kind of play connect the dots with all the saturated liquid points and all the saturated vapor points, you see this shape start to emerge. That shape has a name. In fact, we'll reverse the two. We'll reverse the experiment lines with the vapor dome line. That's what it's called, is the vapor dome. And under that dome, there is a saturated mixture of vapor and liquid. So there's saturated liquid and saturated vapor. They're in equilibrium with one another. To the left of that line is the compressed liquid region. To the right of it is the superheated vapor region. And I wish that we had a region above the critical point just called the critical region, but we don't for whatever reason. So the right-hand line from the critical point down is called the saturated vapor line. The line from the critical point to the left is called the saturated liquid line. And as I said before, when you have a mixture, this is what the first graphic's all about, when you have a mixture, none of the system's mass is at the average specific volume of the system. Rather, all the liquid is at the saturated liquid specific volume and properties, and all the vapor is at the saturated vapor properties. That was so much fun, just like Sharknado, which I believe now has a cult following. I don't know why anyone would want to see sharks coming out of a tornado. That's such a crazy concept, but I think Mythbusters even performed an episode on that. Anyway, they at least mentioned it, I'm pretty sure. What if we boiled water but in a different way? What if we boiled water trying to hold the temperature constant? Could you boil water at constant temperature? Actually, you can. All you have to do is control the pressure very precisely. So let's say we put the water at 150 degrees Celsius and start adding thermal energy. And as we put thermal energy in, we pull weight off the top. So we're changing the pressure. We're reducing the pressure on the system. Well, what will happen is we will finally get to a seemingly magical pressure of about 0.48 megapascals, where we no longer can remove any sand from our pile because the temperature will naturally remain at 150 degrees, and there will be a phase change that begins as it goes from liquid to vapor. And so we'll just leave the pressure constant until all of the liquid has boiled off and we now have a saturated vapor. And then if we continue to add thermal energy, and we want it to be at constant temperature, then we better start removing some more pressure or more mass to reduce the pressure on the system. Now, removing the mass only helps us if we're on Earth, where gravity is acting on that mass, pulling it down, providing a weight, which then gets distributed over area to become a pressure. I don't want you to think that I'm confusing those various concepts, and you shouldn't either. But we would remove mass in order to reduce the pressure as we go, so that the temperature remains at 150 degrees. Now, these states are just as they were before. They have the same names. There's the subcooled liquid region in the first state. There's the saturated liquid where it's about to boil. There's the saturated vapor mixture region in the middle. The saturated vapor, no liquid present, obviously, that's about to condense in the fourth graphic there. And then the superheated vapor on the right-hand side. There's still a latent change. The changes from subcooled liquid to saturated liquid, even though we're holding the temperature constant, are still referred to as sensible changes, even though it may not make sense to you that the temperature is changing. Since the pressure is changing independently of the temperature, it's still called a sensible change. And then during the constant pressure heat addition process, that is a latent change, and then again we have a sensible change in going from the saturated vapor to superheated vapor. So we could play the same game that we did last time and draw the vapor dome on a PV instead of a temperature versus specific volume diagram. And you can see the various experimental curves where the pressure has to be reduced to maintain temperature constant. So these are the dotted lines are both lines of constant temperature, but obviously two different temperatures. And you can see that connecting the transition points where there's a beginning of a latent change, a phase change, connecting those points together yields the vapor dome again, and will yield the critical point and everything, and so as it was. Everything's named the same way. The superheated vapor region's off to the right, the saturated liquid vapor region's under the dome, and the compressed liquid region is off to the left with a critical point at the very top of the dome. We can extend the PV diagram or even the TV diagram to include a solid phase, but it depends on whether the substance expands on freezing or contracts on freezing. Most substances get smaller when they freeze. Water, on the other hand, right at the freezing point, it starts to turn around, it starts to change, it starts to get bigger. The ice crystals are a little less dense than the liquid, and so their specific volume actually changes. So these can be a little bit difficult to understand, but you can see on both of these that there is a region where the pressure is low enough such that solid and vapor can be in equilibrium with one another, and this is called sublimation. You may have seen it with dry ice, for example. You may have done an experiment in chemistry class where you had a vessel that you put ice in and you reduced the pressure so much. We did it in chemistry class with running water in Venturi. Well, where you've reduced the pressure so much that the solid sublimates. It changes into vapor, and if it's in equilibrium, the vapor can change back into solid directly without going through the liquid phase. Now, the pressure versus temperature diagram, I showed you a little bit of this before where I was showing you the saturation, pressure, and temperature, but that was up on, see where it says vaporization from the triple point all the way up to the critical point. That was the section of the curve I was drawing. I actually didn't take it down to zero pressure. And so if we extend that diagram a little bit more to lower pressures and temperatures, then we also can see sublimation at relatively low pressures where solid and vapor move back and forth by deposition and sublimation. Now, if we have a substance that contracts on freezing, you can see the melting line that's solid, but if it's a substance that expands on freezing, the melting line moves to a different area, really, of the graph. And then you can see vaporization, the vaporization line, which separates the liquid from the vapor region. Now, above the critical point, we've got supercritical fluid. We can't really call it a gas or a liquid, it's just a fluid. But you might wonder, well, I see pressure, I see temperature, we were using volume a minute ago, can we put all of these together? Yes, we can, and these are the surfaces I prefer because it helped me understand saturation of what it is and what we're doing here. At first, when I saw these solids, I thought that the substance, say water for example, so on the right hand side surface, I thought the water, this is back when I was a student, I thought the water could exist at any point within the within the solid. That's not the case. The water has to exist at any point on this surface. Now, the reasons why, at this point, I couldn't tell you exactly why water behaves the way it does and water shapes its PVT surface the way it does. That's just the nature of water. And if you deal with a different substance besides the chemical H2O, it will have a different surface. Why that is probably has something to do with quantum chemistry. I don't know. We don't really care. It doesn't matter. As engineers, what we want to do is use substances that have useful properties. And what does that mean? Well, that means that they behave in a way, they have a PVT surface that is useful for our process. That's all we really care about. So all we need to do is quantify the behavior of these various substances and then select the one that has a PVT surface that is beneficial to our process. Now, obviously, there's more than that to it. Obviously, chemical properties and things, if you're doing chemical reactions, are important. It's not a good idea to use ammonia, for example, as a refrigerant in a car or a house, even though ammonia is a very good refrigerant and works great in industry, in very large freezer areas. The problem with it is that it's toxic, right? It has a property that, yeah, it has a nice PVT surface, but it'll kill you, right? So unless you can afford to constantly monitor for unknown or missed releases of ammonia, it's not a good idea to use a toxic substance to to have your air conditioner work so you can be cool in the summertime. Probably not worth it. The other thing here is that we may not really care about the entire surface. For example, there's a project I've wanted to work on for a long time. Back when I was a kid, I thought, the summer's so hot and the winter's so cold, wouldn't it be nice if we could save summer's heat somehow and use it in wintertime? Turns out the ground does that automatically for us, right? The ground temperature is around 55 degrees or so in this area year-round if you get down deep enough. So geothermal systems work very well for heating and cooling buildings and homes and things. They're very efficient. They'll cut your costs down tremendously. It's amazing how cheap geothermal heating and cooling can be. The problem with geothermal is that you have to put a big heat exchanger in the ground, and regardless of how you do it, it ends up being relatively expensive. It's usually the most expensive part of the installation, easily costing $20,000, especially if you go with vertical boreholes and a nice vertical loop system. So you can access temperatures, well into the earth. Well, on the scale of the earth, barely into the earth, but still 200 feet down or so is a pretty good distance, I guess. That's a problem. Well, the sun still shines in the summer. Is there something else we could put thermal energy into? Turns out there is. And I have not looked into this much yet, but it's something I'd like to play around with. The problem with it is that it uses corrosive chemicals. So these are chemicals that can chemically burn your skin. They obviously are hard on whatever piping you run them through, and you have to be able to pump this stuff around. But basically the property that makes this useful is that it has a phase change at a relatively high temperature, and it has a relatively high heat capacity, so it can store a lot of energy. And so basically, if you had a decent sized vat of this stuff, you could pump a heck of a lot of thermal energy into it during the summertime, and then in wintertime slowly siphon off that thermal energy to heat your house. And that's a lot more convenient than putting a heat exchanger in the ground for 20 grand. It could possibly be a whole lot cheaper depending on how much the chemical costs and how difficult it was to control it, and if there were any spills, obviously there's cost for cleaning that up, and you want to avoid that in the first place, so you want to over-engineer it. So as most things, it ends up being a trade-off, but that's something I'm very interested in. It's the properties of that corrosive chemical that make it particularly useful. So if you think about this, it kind of starts to make sense. Basically, the vapor dome, you can see it there. You can see the critical point, the liquid vapor region. You can see the triple line at the bottom of it. You can see that for both types of substances, and that was the vapor dome we were dealing with before. If you think about it, what we were doing is we were looking at the vapor dome from the pressure volume axis. So imagine looking at either one of these straight on from the pressure volume, with volume off to the right and pressure straight up, and you would see what we have drawn so far. On the other hand, you could look at it as temperature versus volume, so that would be looking at it from the top down, and you would still see the vapor dome, and although it would have a slightly different shape depending on the nature of the substance. But now you can see where the various regions are located and how they're actually surfaces that aren't just flat surfaces. We were looking at projections of these surfaces before. And that's why we've got a triple line versus a triple point. If you look at this from the pressure versus volume, you'll see the triple line. If you look at temperature versus volume, you'll see the triple line. But if you look at temperature versus pressure, which, let's see, that would be looking at this from the right-hand side. If you look at temperature versus pressure, you'll see a side view of the triple line. It'll look like a point, and so that would be the triple point. And the triple point is, of course, the particular properties or values of the properties where the substance can be in equilibrium with all three phases, gas, liquid, and solid. Students often get confused about saturation and what it means and what it is. But it's a fairly simple thing. Let's start off with a couple of tricks. So what we were doing before, we were vaporizing water. We were going from a certain amount of liquid and vapor, adding some thermal energy, and noting that we ended up with more vapor and less liquid. Some tricks. If you look at the tables in the back of your book, you'll notice that some of the properties have a subscript G and some have a subscript F. The F and the G come from German words, as I recall, and I don't remember what those German words are. It doesn't matter. Here's the way I remember it. So even though in class, when I say fluid, I mean a gas or a liquid, you probably think of a liquid from your everyday language. And so F can remind you of fluid, which you can think of as liquid, and then G can make you think of gas, and that way you can keep the two separate from one another. It's just a memory trick. But let's look at these two states in a little more detail. I want to drive a point home here. If I were to look at a certain volume in the vapor for state 1, and so you can see the cube there, and I measure the volume and I measure the amount of mass in that volume, and I did the same thing in state 2, notice both of these are saturated mixture states. What I would find is that the saturated vapor has the exact same amount of mass in that volume. As long as I take the same amount of volume, I'll find the exact same amount of mass. In other words, the properties of the vapor are the same regardless of how much there is of it. In the same way, the specific volume of the liquid is the same in both states. It doesn't mean the volume of the liquid is the same, it's the volume per unit mass that is the same. You can think of it as density, because density is just the inverse of specific volume. So the density of the liquid is the same in both states, just like the density of the vapor is the same in both states. But if we were to look at the average specific volume, if we took the whole system, so the whole system volume in state 1 divided by the whole mass in state 1, well, that would be the average specific volume in state 2. That is obviously different than the average specific volume in state 2. I think I misspoke there. But the average specific volume in the two states is obviously different. The mass is the same because no mass has left either container, but the volume has changed. Therefore, the average specific volume is different between the two states. Stated mathematically, the specific volume of the vapor in state 1 equals the specific volume in state 2. Same thing with the liquid in state 1 and state 2, but the average specific volume in state 1 is less than the average specific volume in state 2. So the key thing to note here is that the particular properties of the phase remain constant. The only thing that changes is the amount of the phase. That's it. Nothing else changes. So the total mass in the system is the mass of the liquid plus the mass of the gas. And since the only thing that really changes is the amount of liquid versus the amount of vapor, what we need to do is somehow keep track or define a symbol that will help us quantify how much mass there is in the gas phase versus the liquid phase. In fact, the way we define it to make it easiest is to take the amount of mass in the gas phase and divide it by the total mass of the system. This is a lot like any of the specific properties, right? We take the total volume and divide it by the total mass. So dividing by mass here makes a lot of sense. Of course, it's already mass divided by mass. So if we have saturated liquid and there is 0 mass in the gas phase, then 0 over the total mass will be 0. On the other hand, if we have a saturated vapor and all of the mass, the total mass, is in the gas phase, then the mass of the gas over the total mass, which is the mass of the gas, is equal to 1. So this symbol called X, called quality, we define to be the mass that's in the gas phase over the total mass, and it varies between 0 and 1. And all it does nothing more than just tell us the relative amounts of vapor and liquid. That's really all it does. But it's a very useful property because I shouldn't say property, it's a very useful concept because it helps us to figure out average properties. Okay, it also helps us figure out particular properties, but we'll see that in just a minute. So if I have a system that has some volume of liquid and some volume of vapor, then there's going to be some average specific volume at point B under the vapor dome of the entire system, but all of the liquid is at point A and all the vapor is at point C. Okay, so the total volume, going down to the equations, the total volume of the system consists of the volume of the liquid plus the volume of the vapor, Vf and Vg. But we can represent these as the total mass times the average specific volume for the total volume, and say that equals the mass in the liquid times the specific volume of the liquid to represent the total volume of the liquid, plus the mass of the gas times the specific volume of the gas representing the total volume of the gas. All we've done is just substitutions, right? It's still the same equation. This still says the total volume is the total volume of liquid plus the total volume of gas. Now the total mass in the system is the mass of the liquid plus the mass of the gas. We can rearrange this equation to solve for the mass of the liquid as the total mass minus the mass of the gas. Now if we make a substitution for the mass of the liquid, then we come up with our conservation of volume, if you will. That's what it seems like. It's just total volume equation that relates the average specific volume to the specific volume of the vapor and the liquid and the amount of mass in the gas and total of the system. Now if we divide the equation through by the total mass, then we'll be left with the average specific volume on the left hand side, and the mass terms can be collected together as mass ratios. Now notice that in the first term we've got total mass minus mass of gas over total mass. Well, total mass over total mass is equal to 1, and the mass of the gas over the total mass is a separate fraction. Now you might notice that mg over mt, the mass of the gas over the total mass, has already been given another name, x, quality, right? So we can rearrange this, putting the quality together, and here's our equation that relates the average specific volume to the specific volume of the vapor and the specific volume of the liquid, as well as the quality, in other words the percentage that's in the gas phase by mass. Now a lot of times the difference between the specific volume in the gas phase and the specific volume in the liquid phase is just called VFG. In fact, this so-called lever arm rule is nothing more than an average. That's all it really is an averaging thing. And what it does is it gives you the average property as a function of the individual properties, the property in the liquid and the property in the vapor, and then the percentage that is available. So we could write this not just in terms of specific volume, but in general as any property that we wish. So let's review the volume first of all. We can have two different equations. The average specific volume equals the specific volume of the liquid plus the quality times the difference between the specific volume of the vapor and liquid. That's what that first equation in the box says. But we could rearrange that equation to solve for the quality x as the average specific volume minus the specific volume of the liquid divided by the difference between the specific volume of the vapor and the liquid. And both of these equations are true because they are the same equation. Okay, you don't need one and then you use the other as well. They are the same thing. They're just rearranged. But we can apply this to any property. It doesn't have to be specific volume. We could apply this to a specific volume, to internal energy, to enthalpy, entropy, and so forth. And so what I'd like for you to do is, in your book somewhere, probably with the conversion factors, write down the equations I've got, the two under in general, because they will be very useful to you. Y just represents any property you want to throw in there. Obviously not temperature and pressure. The temperature and pressure of the system is a property more of the system than of the mass. But these deal with properties of the masses. A couple of the properties I talked about might not be familiar to you. A specific volume probably makes sense. Internal energy probably makes sense. But enthalpy and entropy may not. Now, entropy is something we're going to study later. We will put that off for a little while. But let me explain what enthalpy is. Enthalpy is really just a convenient combination of properties where there's one more property that we can't really tabulate. We can and we can't. Let me explain. When you have a volume that is pressurized and you push some mass into it, it takes work to do it. What do I mean? Well, if you consider think of a pipe going into a pressurized container, or better yet, how about some air going into a tank? Okay. Let's think of a certain package of air. There's a pink package there. It has air in it, has some pressure, some specific volume, and it has to be pushed into the control volume. Well, to do that, there's pressure in the control volume, and so we've got to apply force through a distance. You can think of the air behind this package of pink air, whatever that is. You can think of it as a piston that pushes that package of air in. Now, that air that's being pushed in also has some particular amount of mass, and it has to be pushed through some distance. Depends on how much air we take, but we can just take an arbitrary volume of it. And then there's a certain length through which that volume will have to be pushed for that whole package of air to be pushed into the control volume. Think of it as a tank, like I said, in a compressor system. Now that represents work, right? Because if you think about it, the pressure times area is equal to the force that the gas ahead of it has to use to push in, and that force is applied through a length L. It does work, right, to get that package into the volume. So the amount of flow work in pushing this package in is F times L, the force required to push that package in times the length through which we push it. And then that force F is just equal to pressure times area. So we can make that substitution where the flow work is pressure times area times length. Now think about this package again. That length times the cross-sectional area is the volume of the package of air, or the packet of air. So we can make the substitution that A times L is equal to V, the volume of that thing. Now, we don't usually like to talk about how much work it takes to push some arbitrary size. Rather, we'd like to talk about how much work is required to push a unit mass of air into the control volume. So if we take the total flow work and divide it by the amount of mass in that package of air, then we've got the per unit mass work required to push air into the control volume. And so that is called specific flow work. Now, notice that it's PV, but now it's P times little v, where now instead of taking the total volume as we did before PV, now we take the volume per unit mass, so the specific volume. The whole point of all this is that these two things, internal energy, which is more like temperature, and pressure times volume, appear together very often. Now be careful here, because we're going to define enthalpy as the combination of internal energy plus pressure times volume. However, you've got to understand something about enthalpy. Enthalpy is only something that really exists for flowing fluids. It doesn't exist. Now you can tabulate it for other things, because obviously you can talk about the enthalpy of something, and we will, even when it's sitting still, because it has pressure and it has specific volume. But that pressure times specific volume is not energy that a stagnant container has. A lot of people get confused at this point, because they think of a air compressor tank as being something that holds potential energy, kind of like a spring. That's not really true. The thing that an air compressor holds, yeah, it holds mass of air, but that air is under pressure, meaning that it's been squeezed in. And all that really means is that there's thermal energy generating the pressure. You think about it. If you've got a tank out in your garage and the temperature drops, the pressure is going to drop. Have you lost energy? Obviously. Well, what kind of energy has been lost? It's thermal energy, because thermal energy is just really the motion of the atoms on the, or the molecules on the molecular scale, right? That's all it really is. And if the temperature goes down, the amount of motion goes down. Well, you've lost energy in that case. That's really where the energy comes from. All air-powered tools are really thermal energy type machines. They use thermal energy to do their work. Now, it comes out, typically we'll let it flow, and we extract a lot of flow energy from it. But the point is that flow energy and thermal energy appear together when a fluid is flowing. When a fluid is stagnant, you should not think of the energy in that tank as being PV energy, pressure times volume energy. That is a big mistake. And I've seen engineers that have practiced for years make this mistake, but that's not what it is. You can calculate enthalpy from a table where you've got the specific volume and the internal energy of, say, air, and you've got its pressure and specific volume. You can calculate the enthalpy of the air. That doesn't mean that flow energy actually exists, because it's not flowing. The only time the PV energy exists, and you can call it energy, is when it's actually flowing and therefore doing work.